Alright, let's talk about prime and maximal ideals. And this is where things sort of start to get interesting. So we're sort of starting to pick up the pace a little bit. Prime ideals and maximal ideals, I think they're kind of interesting. Anyways, so an ideal, and this is a fancy P, I guess. Thankfully, these fancy letters is just like, at least the ones we've used so far are basically like everything you can do. Like you take a box, and then if you want to make it an A, you sort of add a little bit there. If you want to make it a B, you can go like that. If you want to make it a P, you go like that, and a Q, you go like that. So a lot of these fancy letters, you can draw just like you just use a box and a line. That's all you need, box and a line. So they're not too hard to draw. But if you want to draw them like correctly, then you have to get all fancy. But anyways, so P is prime if whenever you have two elements in our ring whose product is in the ideal, then either A is in P or B is in P. So let's see here. What is something we can prove about this? Turns out an ideal is prime if and only if the quotient is a domain, i.e. if you add if you multiply two non-zero numbers, you'll get a non-zero number. Or two non-zero ring elements, you'll get a non-zero ring element. So to prove this, it's basically we're just using the definitions. So P is prime if and only if this condition holds. But now rewriting this, instead of something being an element of the ideal P is the same thing as it being congruent to 0 mod P. So this holds if and only if AB being congruent to 0 mod P implies A is congruent to 0 mod P, or B is congruent to 0 mod P, and that's exactly what I've written here. But now let's put this in terms of, like, instead of writing these as sort of elements in R modulo an equivalence relation, given by things being equivalent if they belong in the same P coset, let's write them as elements of the quotient space. So like A bar will denote the quotient we get by quotienting the ring by P. So instead of this saying, instead of AB congruent to 0 mod P, we just say that the quotient is equal to 0. So the quotient is equal to 0. This will imply that either A is equal to 0 or B is equal to 0. And of course, these are all A and B. These all have bars over them because they're the quotients. But look at this. This says two elements, the product of two elements is 0. This implies that one of the two elements must be 0. And that's exactly what it means to be a domain. And of course, these are all elements of the quotient ring, and so the quotient ring is a domain. Alright, so we have if and only ifs going all the way through, and so these two things are equivalent. So that's what a prime ideal is. Let's talk about maximal ideals. So a proper ideal, and this is important. So when I say a proper ideal, I mean just an ideal which is contained in the ring R but not equal to R. So this isn't like simple groups where I said simple groups are like a group is simple if it has no non-trivial normal subgroups. I said non-trivial, and non-trivial means not 0 and not the whole group. Here all I'm saying is proper. So this thing can be the 0 ideal, and there will be scenarios in which the 0 ideal is a maximal ideal. But in general, we just need this ideal here to be contained in R but not equal to R. We say that it's maximal if for any other ideal A which is contained in R and which contains M, then that ideal has to be either M or R. Basically, if you consider like, so you've got your maximal ideal and you've got the whole ring, and there's nothing in between the two, or there's no ideals between the two. You can't have an ideal which is like properly contains M and which is properly contained in R. And that sort of makes intuitive sense. So in some sense, there is no... R would be the only ideal which is distinct from M, which contains M. And so, so long as we don't consider R, like if we consider the group of, if we consider the set of if we consider the set of ideals in R which are not R, then a maximal ideal is a maximal element of the set with respect to containment. So there's sort of a Zorn's lemma sort of flavor to this, and some of these arguments will actually involve Zorn's lemma. There are some interesting exercises that use that, and those are kind of cool. So anyways, so now we have a similar proposition to the one we had for primes, but here instead of the quotient being a domain, we have a ring or an ideal is maximal if and only if the quotient is a field. And to prove this, we know by the isomorphism theorems that the ideals in this quotient are in one-to-one correspondence with the ideals in R which contain M. But what are the ideals in R which contain M? Well, that would be the set of all ideals of this form. Any ideal, the collection of all ideals A such that M is contained in A is contained in R. But we know that there's only two of them, M and R, and so this set is precisely M and R. So the ideals in R mod M are in one-to-one correspondence with the set of order 2. So we know that this set has order 2 or size 2. There's two ideals in this set. And let's see here. We know that the 0 and R mod M are obviously going to be ideals in this set. But the set has two elements, and we found two elements, and so these two elements that we found are the only elements in here. And so 0 and R mod M are the only ideals in R mod M. And then we use the fact that this is equivalent to R mod M being a field. And so that's using the fact that basically any ring R is a field if and only if its only ideals are the entire ring and 0. And this is sort of a theorem that's one of the first things that you prove in a ring theory course. Like once you get done with the basic definitions and start moving on to propositions, this is one of the first things you prove typically. And I think because it's a more standard thing, I think we didn't go over the proof. But basically, here's how it works. So if you suppose you have a field, consider an ideal of a field. And so the ideal could be 0, but suppose it's not 0. If this ideal is not the 0 ideal, then it contains some non-zero element. Let's call it R, or let's call it A, because we'll use R to refer to this ring. So we have this ideal, so we have a non-zero ideal of our ring, and we know it contains some element A. But R is a field, and A is non-zero, therefore A has a multiplicative inverse. And this ideal must be closed under multiplication. So if you multiply this element A by its multiplicative inverse, the corresponding product has to also be in the ideal. But if you take an element and multiply by its multiplicative inverse, then you get the element 1. And so what we've shown now is that if you have a non-zero ideal in a field, then that ideal contains the element 1. And once you contain 1 in an ideal, you contain the entire ring, because to get any element, you just take 1 and multiply it by that element, and that has to be an element of the ring, and so in this way you can get every element of the ring. And so this ideal that we started with was the whole ring, or the whole field. So so that means that any non-zero ideal in a field is the field itself, and therefore the only ideals in a field are 0 and the field itself. So that's one direction. For the other direction, you suppose that you have a ring R, and the only ideals in R are 0 and all of R. Now, what do? We want to prove that this is a field. So what we do is we consider the ring generated by, so you choose some non-zero element A in our ring R. And we want to prove that this element has a multiplicative inverse. So what we do is we take this element A and we say, oh, I'm blanking a little bit. I lost my train of thought. I was going so well. We take this element. Okay, so we consider the ideal generated by this element. This is a non-zero ideal, and so by assumption, this will be the whole ring. So basically what that tells us is that you could take this element A and you can get to any element of the ring by multiplying it by some other element of the ring. Because if that weren't the case, then the ideal generated by A would not be the entire ring. Okay, so you can take this element A, and given if you want to take this A and you want to sort of change it into any other element, then you'll be able to find some element of R that you multiply the two together and you'll get that other element. So if we choose this other element to be 1, so that means that A is, the ideal generated by A contains 1. So there must be some other element in the ring such that you multiply this element in the ring by A and you get 1. But that's what it means to be a multiplicative inverse. And so therefore, A has a multiplicative inverse. And this holds for every single non-zero element A of our ring R. And therefore, this ring is a field. And that proves that if you have a ring whose only ideals are 0 and the entire ring, then this ring is a field. And so therefore, we have an if and only if. Alright, so yeah, that would have taken up quite a bit of space to write out. But the argument is sort of straightforward, I guess. Once you've seen it, because I've seen this proof done a number of times over a number of years, so it's sort of like something that you can sort of easily work out. But if you haven't seen it before, I would definitely look it up and or just make sure that you understand how it works, because it's a fairly simple argument, and it's sort of neat. So yeah, so therefore, because of that fact, R mod M is a field, and so M is maximal if and only if R mod M is a field. Is this indeed an if and only if? Yeah, there's no way. I never used, none of these statements that I made were statements that could not be done in the other direction. So this is all good. We have an if and only if. As a corollary, so let's combine everything that we've done so far in this video. So M is maximal if and only if R mod M is a field, but we know that fields are domains, and that should be an easy fact to prove. I haven't thought about this. Why is that true? If you have a field, it's a domain. Say you multiply two non-zero elements. I don't want to try to come up with the proof on the spot here, but this is a pretty straightforward fact in just basic algebra in general. So you either the proof already and you're yelling at the screen okay, why is this guy not able to think of it? It's super easy. Or if you haven't seen it, just look it up. It's not going to be a more than a one-line proof. So fields are domains, and by this domains, R mod M is a domain if and only if M is prime. So this is for a general ring, or this is for a general ideal P. Any ideal is prime if and only if the quotient is a domain. So in particular, R mod M is a domain if and only if M is prime. So what this gives us is M is maximal implies M is prime. And we have this forward direction here. So maximal ideals are prime. And that's an important fact to keep in mind. The other direction doesn't work. There's a lot of really like dumb counterexamples where you have like the zero ideal is it's not uncommon for the zero ideal to be a counterexample. Like just in the integers, the zero ideal is prime because like it's like obvious. If you have well, there's only one thing in the zero ideal, so it's sort of prime for stupid reasons. Because it's really easy to satisfy this if you've only got one element. Well, actually, no, that's not entirely true. It's because... Oh, well, it's because the integers are a domain. And so if you multiply two things together and you get 0, then one of the things had to be 0 because it's a domain. So I think, in fact, in any domain, the zero ring, in any domain, the zero ideal is prime. Because whenever you take two things multiplied together and you get 0, one of the two things will be 0. I.e., if the product of two things is in the zero ring, one of them is in the zero ring. And so the zero ring is prime. However, take Z, and the zero ring is not maximal because you can actually take the ideal generated by any prime will be maximal. Because if you have any ideal which contains Z mod PZ for some prime P, any ideal which contains Z mod PZ and which is not the zero or not all of Z, then it must be the ideal generated by n for some integer n, and n must divide P, and P is prime, so it must either be P. So n must either be P or n must be 1. But that means that n is either Z mod PZ or n is equal to all of Z. Anyways, there's another thing I want to prove before we're done, so let's get going. So we know that we've proven already that we can pull back ideals. It turns out we can pull back prime ideals. So if you've got a ring homomorphism F and a prime ideal in the codomain, then its inverse image is prime in the domain. And to prove this, what we want to do is to prove that P, we're going to define P to be the inverse image. So suppose we have A, B, and P. We want to prove that either A is in P or B is in P. So the way you typically do this is that you assume that A is not in P, then you prove that it has to be the case that B is in P. Alright, so suppose AB is in P and A is not in P. So saying that AB is in P means that F of AB is in Q, and saying that A is not in P means that F of A is not in Q. Alright, so now what? Now if we look at F of A times F of B, since F is a ring homomorphism, this is the same as F of A times B. But we just showed that this is in Q. So we multiply these two things together, and this is in Q. And Q is prime, so one of these two is going to be in Q. But because of this thing, we know that F of A is not in Q. So this is not in Q. And if one of these two has to be in Q and this one's not in Q, then this one has to be in Q. So F of B is in Q. But that's the same as saying that B is in P. So now if that means that if A and B is in P and A is not in P, then B has to be in P. Or in other words, if A times B is in P, then one of either A or B is in P. And that's what it means to be prime. And so P is prime. All right, and that's about it for prime and maximal ideals, at least for now. We'll have a ton more to say about them in the future.